In this chapter, basically, we have made some generalization and we have some examples. So all the concepts are in previous chapters. So we want to, in this example, we want to look at minimum variance linear estimation. Measurement errors, this is just an example. Suppose that we are measuring something, length of an object or weight of an object with n instruments, or with one instrument but independently n times. So in this example, we have n measurements. If we could justify that these measurements are independent and errors are independent, so you could say that xi is ith measurement, and then you have errors. Suppose that errors to have zero mean and different variances, because these equipments could have different standard deviations. For instance, you could assume that you are using a GPS and then measuring a given location n times, but each time you are measuring your location, you have some errors. Assuming that you are doing independent measurements using same GPS or different GPS, you could have different variances. Suppose that you know these variances and we have these measurements. We don't know eta, we don't know these errors, and we want to estimate these eta. Eta is the accurate location. So measurements errors have zero means and different variances. If we want to combine these noisy measurements in order to determine the true value eta. Assume that these errors are independent and we want to use a minimum variance linear estimator. Basically, we want to estimate eta hat by linear combination of, let's say, a1 x1 plus a2 x2 plus an xn. We want to know what should we use as a set of values for these AIs. So what should be these a1, what should be a2 and an. In this example, a minimum variance linear estimator is that, let's say, beta hat is the estimator of eta, which is a function of the observed value, a linear function of observed values, which are these guys. So these guys are measurements or observed values. So this is why we call it a linear estimator. Now, this linear estimator, or whatever values you choose for a1 to an, expected value of these is going to be equal to expected value of the first term plus expected value and so on. Expected value of the first term, because a1 is a constant number, becomes a1 expected value of this eta, and so if you add them, you can get this one. Obviously, not always, for not all values of AIs here, this is equal to the true value. Okay, this is not always equal. The difference between this value, the mean of your estimator, and the true value is called bias. So bias is equal to the difference between the true value and the mean of the estimated. So we call the difference between the mean of the estimate and eta as bias. Now, we call an estimator unbiased if the difference between the mean and the true value is zero. So the estimator is called unbiased if the bias, which is this guy, is equal. If mean of beta hat is equal to beta, is equal to the true value of your unknown. We call it unbiased. So as soon as I say unbiased estimator, we call this. So we are looking for minimum variance unbiased linear estimator. So this is a linear estimator. This is bias. Unbiased means that mean of the bias is equal to the true value. Now, if beta hat is an unbiased estimator, then we should have, if we want to have unbiased estimator, so mean of beta hat, which is equal to eta summation of AI, I equal 1 to n, should be equal to eta. I simplify this as that. So if I say that beta hat is an unbiased estimator, I should have these conditions. So sum of these guys, sum of AI should be equal to 1. So these means unbiased estimator.